Okay, folks, we're getting toward the end of chapter 1, this very, very long and detailed chapter. We're going to wrap it up with 2 sections on coordinate geometry. We're going to be skipping, I think it's section 9. So we'll do section 8 and then section 10, and then review and have a test on that. So today, a lot of what you see today, and especially in our next lesson, if you had any kind of a decent algebra course at all in high school or a decent geometry course, many of this will bring back very, very, very fond memories because we're going to be doing a lot of things that you've seen, and I'll be going through this relatively quickly because I'm assuming it is so incredibly easy for you, hopefully. So let's talk about graphing, okay? We will be graphing using an X and Y axis, but actually the axes could be anything. Here I've made a graph. These are the days, and this is my happiness scale. And you'll notice on day 4, I discovered bacon. Oh, yes. And my happiness shot upward, okay? So we're going to be graphing on coordinate planes like that. It would be very, very helpful to have graph paper. You can call it a coordinate plane with an X and a Y axis, or as in this case, a T and a P, or a day and a happiness, all right? But oftentimes it's also called a Cartesian plane in honor of René Descartes, Cartesian, who was a Frenchman, a French mathematician and philosopher. And he's the guy who said, I think, therefore I am. All right, so let's talk a little bit about what you can see here. The naming of the coordinates, the naming of the quadrants, pardon me. Quadrants there are 4 quadrants here, 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 and here, okay? You start in this quadrant, the upper right. This is Roman numeral number 1, quadrant 1, Roman numeral number 1. Roman numeral 2, Roman numeral 3, and Roman numeral 4. Okay, they go counterclockwise, 1, 2, 3, and 4, written with Roman numerals. All right, so we're going to talk about quite a few things here with regards to coordinate geometry. Find a distance from the blue point to the yellow point in 2 different ways. Okay, one way to do the distance from the blue point to the yellow point, it looks like it's the hypotenuse of a triangle. And this is indeed a right triangle here that has this side is 4 and this side is 2. I'm just curious how well you folks can see all of that. Well, it's a little faint, but hopefully you're with me. This is a right triangle. This side is 4, this side is 2. So one way to do it is to do 4 squared plus 2 squared equals good old Pythagoras. Pythagorean theorem, 4 squared is 16, 2 squared is 4, c squared is 20, so c has to be root 20, okay? And you can find a decimal for that if you like. Now, the second way is to use the distance formula. Actually, what we did here, when we found the 4 was how much the y values changed. The 2 was how much the x values changed. The distance formula in coordinate geometry, d is equal to, here it is, x1 minus x2 squared, y1 minus y2 squared, okay? This is essentially the Pythagorean theorem, because look what we did. We squared the change in the y values. We squared the change in the x values, added them together, and then took the square root. Okay? So really, this is what we did right here. So the nice thing about the distance formula is if you don't have a picture, what if you just have the coordinates? Like, for instance, the coordinates here are back 3 and up 2. So the yellow point, yellow is -3, 2. Okay? Back 3 and up 2. The blue is back 5 and down 2. So the blue is back 5 and down 2. All right? So the distance formula you can do without a picture. You can simply subtract the x values. -3 minus a -5 is -3 plus 5. -3 plus 5 is 2, so I have 2 squared. Subtract the y values. 2 minus a -2. 2 minus a negative is plus a positive. It's 2 plus 2. 4 squared. Precisely what we had up there. And it's the square root of 20, once again, for the distance. Okay? So there are 2 ways you can find the distance between 2 points. If you have a picture, or draw a picture. If you have a picture or you want to draw a picture and do it by Pythagorean theorem, or if you just have the coordinates, you can simply subtract x's, square it, subtract y's, square it, add them, and take the square root of the answer. Okay. Find the distance from the green point to the red point. Because we have a picture, I'm just going to do Pythagoras. Green to red. Green is over 2. So this distance is 2. And then I'm up 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's over 2 and up 9. Pythagorean theorem, 2 squared is 4. 9 squared is 81. C squared is 85. So C has to be root 85. A little bit more than 9 units. How about midpoint of the segment connecting the blue to the green? Now, we already have the blue coordinates here, -5, -2. Let's talk about the green point. It's over 1 and down 5. So over 1 for green is over 1 and down 5. Okay? If you want the midpoint, now think about this. Here's the segment going from blue to green, right here. Wouldn't the midpoint be somewhere right in the middle, right? Be somewhere right in the middle. So I want in the middle of the green and the blue. How do you find the middle? Like for instance, supposing you did really good on the first pre-calc test and you got a 95. Supposing you didn't do so hot on the second one and you got a 70. How could you find your grade so far? You find the point in the middle. You find the average. You add them and divide by 2. Okay? So that's what we're going to do to find the midpoint of the line segment connecting blue to green. What I want to do to find the midpoint, I want to add the x's, divide by 2, add the y's, divide by 2. Okay? Just finding an average. So take the x's of the blue and green, 1 plus -5, divide by 2. Take the y values, -5 plus -2, divide by 2. Or I'm going to get -2 for this one, and that's -7 divided by 2 is -3.5. There's my point. If I come back 2 and down 3.5 is right there. And doesn't that look like the middle of the blue and the green segment? You bet, it is. Okay. Moving on. Parallelogram has vertices. All right, let's make a picture. Okay, so we have one vertex at 0, 0, one at 2, 5. So I'm going to go over 2 and up 5. This would be much, much easier to do on graph paper. Then I'm going to go over 8. And I'm going to go up 5. So over 8 and up 5 would be right about there, I think. Okay? And then 6 and 0. There are, yeah, it doesn't look too bad after all. There's my parallelogram. Okay, let's put the points in here. 0, 0, 6, 0, 8, 5, and 2, 5. Right? Show the diagonals cut each other in half. They bisect each other, cut each other in half. We want to find the midpoint of this one and the midpoint of this one, and it should be the same point if they cut each other in half. 2 plus 6 is 8, cut it in half, 4. 5 plus 0 is 5, cut it in half, 2.5. 8 plus 0, 8, cut it in half, 4. 5 plus 0, 5, cut it in half, 2.5. Both diagonals intersect at the point 4, 2.5, which is the midpoint of each diagonal, so they cut each other in half. Pictures, draw pictures. Okay, a circle has a center. If there's one thing at all that's interesting or somewhat difficult in these last two sections we're going to do in chapter 1, it's equations of circles. Some people struggle with this. A circle has a center at 4, 3. 1, 2, 3, 4. 1, 2, 3. Here's the point 4, 3. Now, has a radius of 5. I don't care where you go. If we go up 5, if you go down 5, which because we're up 4 here, down 5 would be down about here. You could go over here 5, which would be, I guess my picture's not drawn too well. Okay, if I go over here 5, I'm actually, wait a second, this is only up 3, sorry. So 5 would be down, now it's much better. 5 would be down 2 more. And then 5 this way would be like over to here and over to here, and you're going to have points. The distance has got to be 5. Okay, all of these distances are 5. All of them are 5. What are these points? I don't know. Let's just call these points x, y. Okay, let's call these points x, y. I know the distance between these points is 5. Right? Everybody be able to see that clear enough? Okay, it's close. I better not write any smaller. All right, if the distance is 5 from here to here, let's use the distance formula. The distance formula says that you subtract the x's, okay, and square it. You subtract the y's and square it, okay? And if you do that, you will get the distance, which is 5, the radius. So I'm going to put a letter R, okay? How do I get rid of a root? Don't I square both sides? If I square this, look what I get. I get R squared equals x minus 4, y minus 3 squared, x minus h, y minus k squared, where hk is the center of the circle and r is the radius. All right? If you use the distance formula here, I get the equation of this circle will be, because this radius is 5, I'm going to square both sides. 25 is equal to x minus 4 squared y minus 3 squared. Okay? That is the equation. Every point on that circle, if I put it in there, will make a true statement. No other points anywhere out of all the millions of points will make that true. Just the points on that circle. All right? Notice it has to be x minus 4, y minus 3 if the center is 4, 3. If the center would be 4, negative 3, down here, 4, negative 3, it would be y minus a negative 3, or y plus 3. Okay? So be careful of that. Here is the general equation of a circle. You're going to have to know that. You're going to have to know how to use that. And I'll go through some problems down here to show you how to do this. All right. Okay, so how about an easy one to get started? We want to graph that equation. It's in perfect form. Perfect form. I know the center. I know for the y value, the center is 5. But the x value has a plus sign. Let's change that plus sign to minus a negative. 2 negatives make a plus, right? So x minus a negative 3, y minus 5. The center of this circle has to be at negative 3, 5. Negative 3, and 5. So it's right about there is the center. Negative 3, 5. The radius is 4. So it doesn't come the whole way down and touch here, and it goes over here and it laps here. Here is the circle. Okay? This one is a real easy one. I'm going to write it a little bit differently. How about I write it x minus 0 squared, y minus 2 squared equals 4, yeah? So isn't the center of this one at 0 and up 2? And it has a radius of 2, okay? Radius of 2. So it's 0 and up 2, and it has a radius of 2. The center of this one would be here. Radius is 2. There's that small circle, is this one. Okay? All right. One step trickier. How about this last one here? Find the equation of a circle with a center of 2, negative 1 and a radius of 11. Oh, this is an easy one. We know the general equation is that. So it would be x minus 2 squared, y minus a negative 1 squared equals 121, which is 11 squared. Okay? Do they get any more interesting? Oh, yes, they do. Show that this is a circle and sketch it. Don't worry about these yet. Show that this is a circle and sketch it. I want to get it into this format of x minus something and y minus something squared. I want to get quantities squared. Complete the square. If you complete the square, so let's do it. I'm going to group the x's, x squared plus 2x, y squared minus 6y is 7. Okay? If you complete the square, we all learned how to complete the square. This, you cut in half, is 1 squared. Now, check your work. X plus 1 times x plus 1. Can you do that in your head? X times x, x squared. Check. Outers, 1x. Inners, 1x. 1x and 1x, 2x. 1 times 1 is 1. There's a 1 in there, but there is no 1 up there. I got to get rid of that 1. Minus 1. Okay? Let's go over here. Complete the square. Cut that baby in half. Y minus 3. Yeah? Check your work. Y minus 3 times y minus 3. Y times y squared. Checks. Outers, negative 3y. Inners, negative 3y. Negative 6y. Checks. Negative 3 times negative 3 is 9. There's a 9 hidden in there, and there's no 9 up there. We got to get rid of the 9. Equals 7. Okay, so now what have I got? I'm going to write this as a minus. X minus negative 1, yeah, plus y minus 3. Negative 1 and negative 9 is negative 10. I'll add it to the other side. This becomes 17. I have it now in x minus h, y minus k equals r squared. Center of the circle is negative 1, 3. There's the center. Negative 1, 3. The radius is the square root of 17, which I know is a little bit bigger than 4. Square root of 17, 4.1. So the radius is 4.1. If we sketch it, we have, I better draw the coordinate plane first, don't you think? My center is at negative 1, 3. So negative 1 and up 3. So there's my center. The radius is just a bit bigger than 4, so it's going to come down in here, and it's going to come way over here. So the center is going, the center's up there, so the circle is going to be something like that. Okay? All right, last thing I wanted to do with you was to check you out on symmetry. Do you understand symmetry? Let's talk about symmetry. We want to talk about symmetry that Is a shape symmetrical about the y-axis? Is a shape symmetrical about the x-axis? Is a shape symmetrical about the origin, just this point in the middle? And it's possible something is not symmetrical at all. Okay, like for instance, this red graph right here. If I fold that over, this is the exact mirror image of this. Yes? You fold that over, this would be symmetrical about the y-axis. I hope you can see those pictures. They're a little faint, but I think everybody can catch on what's going on here. This is symmetrical about the y-axis. Same thing here. This is a mirror image of that. This is symmetrical about the y-axis. Now, look at this. Everything here is the same as everything up here. Okay? This is symmetrical about this point. For instance, to go from this point to get up here, you go up and over. You go up and over. Okay? This one is symmetrical about the origin, 0, 0. And by the way, we didn't really talk about that, but I'm assuming everybody knows 0, 0 is the origin. Look at the red and the blue. Once again, symmetrical not around the y-axis or the x. The blue is a reflection around that point. So it's symmetrical around the origin. Bingo. Same thing here. This is symmetrical around the origin. These go down, these go up. This little one up here is this little one down here. Symmetrical about the origin. There's another one. Symmetrical about the origin. It flips and goes up in the diagonal quadrant. How about this one? Whoa. This one is symmetrical about this line. That's not the y-axis, it's not the x-axis. So technically, of the three we talked about, the origin, the x-axis, or the y-axis, this one is not symmetrical about anything. This one, though, is symmetrical about this line, which is x equal 2. Okay? How about this interesting looking graph? This one, by the way, this is not a function because it fails the vertical line test, right? This top part is a reflection of this bottom part, and the bottom part is a reflection of the top part. It just folds perfectly. This shape is symmetrical about the x-axis, okay? A lot of fun with symmetry. Here is your homework. One extra problem. Make sure you make a table, put all your information in it, and you should be able to solve that. Check out the assignment down there on page 92. From 7 to 59, you do only those problems ending in a 7 or a 9, like 7 and 9, 17 and 19, 27 and 29. You with me? That's all I want you to do down there, just to get a flavor for what's going on in these problems. All right? We will conclude this chapter our next time together.